record on this computer. We are now live and recording. Exam 1 practice. I'll let it open it with Firefox. Okay. Actually. So now new share exam 1 practice. Here we go. Here's a file. So this is what it would kind of look like on paper. Let's go ahead and get started with this. All right, so this is so first question. This is a doubly linked list. Assume each node has a variable storing their memory location denoted by the letter on the node. So node A, B, C, D. So for each of the following questions, please indicate which node is being referenced by the chain of variables. This is actually fairly easy. So D dot previous dot previous dot next dot previous. So the answer would be B. Okay. Next, C dot next dot previous also B. So B and B, and now B dot next dot prev dot prev dot next dot prev dot next dot prev. But what we see here is that we aren't going out of bounds at any point, so we can just simply cancel. Next, and prev cancel, and next and prev cancel, and next and prev cancel. So we're also at B. Amazing, they're all B. Wonder if that was intentional. Yes, it was. Okay, so all three of those answers were B. All right, write a sequence of commands that will remove the tail of a doubly linked list. So this is gonna, something like this will be on the exam, where there's gonna be drawing involved. If you have to draw something, you'll just simply, you can either just take a picture of it and upload it, or take a screenshot and upload it, but there will be a drawing question involved with, then that will require you to upload something. All right. So write a sequence of commands that will remove the tail of a doubly linked list. So again, a lot of times this is easiest if we draw this out for ourselves. So we got ourselves we don't have to draw a full doubly linked list, but it is useful to have a good amount. So I'm just going to put dot, 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 because again, we don't really care about the front. If we've got the tail, then this is what we need. So what do we need to do to remove the tail? So what we would need to do is we would need to make this guy the new tail. Okay, and set up so that nobody was referring to him. So what we would say is that this node over here should be the new tail. So the tail label should go to who? It should go to which node? The node that's denoted by tail dot previous. Tail. Okay, and then the next one we need to do is that we need to, well, the tail needs to point to null. So, sorry, the thing that comes after the tail should be empty in a regular doubly linked list. So tail.next is equal to null. And that will remove that. And now that nothing is referring to this node, it will get garbage collected and automatically removed for us. All right, using a linked list with 3 nodes, draw what happens to the list as each line executes when you remove the tail. We actually just kind of did that, just in reverse. All right, write a sequence of commands that will add a new item to the beginning, to a new item to index 0 of a doubly linked list. And then using a node, link. Yes.
Sorry about that. My internet cut out. So for number 4, all we would have to write is that tail equals tail.previous and then tail.next equals null.
Yep.
Okay.
For that one, because it's not circular. All right. So now let's go ahead and write a sequence of commands that will add a new item to index 0, and using a linked list with 3 nodes, draw what happens as each line executes. So I'll go ahead and draw it up here, even though that's in the wrong space, but that's, again, just space constraints. We all know what's going on. So here we go. We've got 3 nodes. It is a doubly linked list, but on your exam, the things will be singly linked lists for simplicity's sake. Okay, so head, head.
So there aren't going to be any questions regarding the doubly linked list.
Nah, because they take so much longer to code.
Okay. Thank you.
So we want to add a new item, and here this is answering number 2 first. And so simply what we're going to do is we are going to do step 1, attach the new node, right? So we have this new node, this new item. So I'm going to call it node E adding is equal to new node. Yeah, I know my handwriting's terrible. Just bear with it. I swear I'll type for the other problems. And this would take item. All right, but that's okay. And then we say, but here's the important part. Adding dot next equals head. And that's going to do this actual attachment over here. Okay. Now the head needs to, now we also need to connect this guy. So we say the current head, it needs to connect up. Head.previous is equal to adding. Because it's a doubly linked list, there's a lot of ways we can do this one, because there's less ways we can break it so that we can not. With a doubly linked list, it's much harder to break it and make it so that it's irrecoverable. Oops. Okay, and now the final piece is head is equal to adding. And so we just take this and move head over to here. Got it? Okay, so those are those 2 problems for your all drawings. And now scroll down. All right. You'll have a question kind of like something you'll see in exam that you saw in the second worksheet. So suppose you have a list of integers. Write a method that finds the minimum and maximum values and returns their sum, regardless of the implementation of a list. That should be static on this, but whatever. Okay, so. Okay, so we are going to stop sharing. Actually, I'm going to go ahead and share my entire screen now. That seems much easier than much easier than trying to do all this. Okay, let me just, share my screen. There we go. So, and there we go. So we're going to copy this over, new file. Okay, and paste. Okay, and now fix it up. So public static int min plus max takes in a list of integers. Int min is equal to this. Okay. Okay, there we go. Import class. Util. Okay, so a couple things first. You'll notice that it is that I said int min is equal to integer.max value and int max is equal to integer.min value. There's a bunch of ways I could do this. I could have also done list.get0 for each of them, but I didn't want to actually write that out on an exam because it reminds you about what get does. So what does this mean? Well, min is equal to the max value. What is max value? It is 2,147,000,000 it's all this, it sounds pretty random, but it's actually 2 to the 31 minus 1, which is the largest value that for a so basically any integer will be smaller than this one unless it's the biggest value possible. Okay. Similarly, max is equal to negative 2 billion, which is negative 2 to the 31. Now you might be wondering, wait, why is this 2 to the 31 minus 1 and this one's just negative 2 to the 31? And the answer is it's not evenly split. There's a because of 0. If you're curious about this kind of thing, look up 2's complements if you haven't learned about it. 2's complement is the way that binary encoding works with being able to add positive and negative numbers. It's super clever. So anyway, anything that we have will be smaller than max and bigger than min. Okay, so what all we're going to do here is I'm actually going to do this a couple different ways because of problem number 9. What is the time complexity of this algorithm? Okay, this may seem fairly straightforward, but it's actually not based on your assumptions. So for int I is equal to 0, I is less than list.size. Item is equal to list.int, I'll call it num, is equal to list.get I. So we'll get the ith item. Okay. And then we will get the and then what we're going to do is say, hey, if num is greater than if num is greater than the max, then that is our new max value. Max is equal to num, right? So if this number is bigger than what we've seen, is the biggest number we've seen so far, it becomes our biggest number. And if this number is smaller than the smallest value we've seen so far, it becomes the smallest number. Min is less than, min is equal to num. And that will return min plus max. Make sense to everybody? And this is all we need. Okay, so well, I'll do this again another way in a minute. What's the time complexity of this algorithm? Well, it depends actually on whether or not you're using an array list or a linked list because of this get method. This get method works in constant time for an array list. So if you're doing an array list, you're just checking you're doing a constant time lookup for every single one of the n values in the array list. Make sense? So you're grabbing into 0, 1, 2, 3, 4. Each of those takes constant time. So each of the n items has a constant time lookup and then 2 checks, which is equal to, so say, call it 3n, right? Whatever. But that's O of n. But on the other hand, if we're doing a linked list, get takes O of n time, right? Because you have to iterate to that location. So that's going to actually take, so we have so this loop runs n times, and now we have an O of n operation in it. So each of the n items runs n time, has an O, needs to perform, each of the n items has a corresponding O of n operation. So n times n would be n squared. So it would run, so this particular way I wrote it would run slower for a linked list. However, I can do it O of n for both if I use an iterator specifically, but I don't have to write an iterator myself or do any of that stuff. The for each loop just simply will use the iterator. So e num, except we know what e is. We know it's an integer. So int num for every num in list. I don't know why it wants me to do it like that, but okay. For every number in the list, And then just copy these 2 lines.
Bless you.
Ow, that hurt for some reason. Give me 1 second. Okay. Okay. So this now, because it's a for each loop, and we'll use the iterator and basically save its place and iterate through something in O of n time. So it does the getting for us. This just takes O of n time for both the array list and the linked list. So the for each, so long story short, if you want to be runtime efficient for a linked list, then you use the for each loop. If you want to go through each item. So not always possible. Especially if you're working in a static method and you don't know what kind of list it is, because so it's not always possible to use access the individual nodes, because we're in a static method here. So we don't have access to any specific list. And we don't know what kind of list it is. Remember, nodes are private. You can't really access them outside of, unless you're inside the linked list class. So suppose you have a list of string, write a method reverse words that returns a new list with all the strings reversed. So here I'm saying hello world nice becomes Ola, Dulral, and Echen or Echen. All right, so reverse words. And so here the kicker is that we are creating a new list. Now, if we weren't making a new list and having to replace everything, that would be much more difficult. Or much more annoying, but here we're just making a new list. So, okay, and I didn't give a return here, so let's go ahead and write it. So, and let's bring this up to the top of the screen. All right, so, and let's do this in view, appearance, distraction-free mode. There you go. Nice and minimalistic here now. Okay, so list, we know what it's going to be. It's a list of strings. Output, and this will prevent us from accidentally like stuffing an integer in it. List of strings output is equal to a new, well, we got to have some kind of list. We can't simply say new list. So I'm just going to do array list because I can. I could easily do a linked list. In fact, if I'm adding to the end, a linked list will be superior. So I'll just do a linked list because I can. It really doesn't matter though at the end of the day. So now I'm just going to use the for each loop because I don't care what index everything appears at. As long as you don't care what the index is, you can use a for each loop. So for every, and I like to make my variables make sense. For every string word in the list, right? Then I need to reverse the words. And then when I'm done, I'm going to return output. So what I'm going to do is, so I need to make a string. So there's again a couple ways I can do this. String reversed is equal to an empty string. And now what I have to do is I have to go through every letter and reverse it. So there's again multiple ways to do this. One way to do this is our standard way, which is for every so for every character in the string, what we're going to do is we are going to start at the end of the word dot length. I hate this about Java, by the way. The length of an array is dot length. The length of a string is dot length with parentheses, and everything else is dot size. Python, you just have one function, which is len. So for in I word dot length is equal to, so we're going to start at this index, and we are going to go while I is greater than or equal to 0, I minus minus. And basically what we're going to do is say reverse is equal to plus equals word dot car at I. This is going to get the last character. So reverse everything by simply going in reverse and concatenating. Make sense to everybody? Another way to do that, rather than doing a weird reverse for loop, is to change the way we add it. Like this. And simply we're going in order, but what we're doing is we're adding it in front of everything we have already. So it would be, so for hello, it would be H, and then it would be EH, and then it would be LEH, and then LLEH, and then OLLEH. Make sense? So, and by the way, once we have our reversed, we should totally add that to our list, to our output, so we don't forget output.add reversed. So that's another way to do this. By the way, these all take, this operation will take, no matter how I write it, O of n time, as long as I'm doing it with this for each loop over here, because we're going through n strings. That's one way to do it. Or I'm parsing through a total of n characters, and I'm touching each character once. Okay. Finally, there is one other way to do it if you know a bit more of Java internally, which is we can do this in kind of a hilarious one-liner over here, which is that we can do and this is awful, and you shouldn't do it like this. You should break it out into multiple lines, but new string, we could do new string builder, which is an older class. I think it's been replaced by another class in Java, but whatever. String builders take strings and build them. So I'm going to pass it word, and I'm going to build a string from word. And then, but it's giving me an error because that's not a string, so I'd have to return a string. But it has a nice reversed function. And why does it not like me? Because provided type string builder, reverse it and then dot toString. And there we go. One liner that would do it, but don't do it like that. But the string builder can, if you were to do it, it would be simply like string builder reversed is equal to new string builder. And we're building the string from word, and you can add other things to the string builder to build it from. But I'm just going to build it from word, and then I would just simply do reversed dot reverse, which returns the string builder, but now it's been reversed. And then I would do toString, which outputs the string builder, the string that the string builder has been building. Hold on one second. My dog really wants to come upstairs. Once I'm done going over this exam, I might step off for a second and migrate downstairs, because it is starting to get a bit warm up here. We have the insulation installed, but with no AC on this side of the room, it does get into the 80s here, so it kind of gets a bit toasty. So, all right, so what is the runtime complexity? I already said O of n. So write a method called delete list, which removes all items from a list, making it empty. Okay, so this will be inside of a list, which means it's inside, it's there. So you've had access to the head, the tail, and optionally the node. So if it was singly linked list, this would be easy, but it's a doubly linked list. So we've kind of got an annoying thing to do. So how do we do it? It's not a matter of just making head or tail null, because since we're in a doubly linked list, they would each refer to each other. And I don't think that would just simply, delete, get garbage collected like that. So what we have to do is, let's see, we need to do, can't really do for loop. So we just simply would say, let's write a while loop. While head is not equal to null, and I'm not going to worry about tail since the tail is optional, it says. While head is not equal to null, head head is equal to head dot next. So move over to the next one. What's up? Are you telling me yet? Hey, Annie Ray. Happy Feet came upstairs to bark at me to tell me that she needs to go out again. Annie? 1 second. Sorry. I feel super important. The dog came all the way upstairs to tell me she had to go to the bathroom. All right, so head is equal to head dot next. So what did that do? That we've got this kind of thing going on here. All right, and I'm going to be, so we've now just migrated the head from being this node to being this node over here. So now let's go ahead and detach everything. So head, so the thing that was formerly the head is now head dot previous. And we want, let's go ahead and make his next pointer not point to anything. Head dot previous dot next is equal to null. It's probably unnecessary to do that, but hey, I'm kind of being a stickler here. And then we're going to say, hey, head dot prev is equal to null. Ta-da. So that will erase that. This guy will get garbage collected. And now it's like this guy was the head all along. So, and we just do that until we don't have until head points to null. Except that, wait a second, head is equal to head dot next. Hold on a second. Except that if we, so we kind of come into an issue though. So if we get over to here where we've got our last node, we get into a bit of an issue. So we need to say head dot next is not equal to null. So now we will stop when we get to the when we have one node left over here. Okay. So now this will stop when we have one node left, because we can't go head is equal to head dot next and then start saying, hey, move the pointers around. We'll get a null pointer exception. Now that we're at the end, we just simply say head is equal to null, size is equal to 0. Now we're done.
So is that outside of the loop?
Yes. Yes, this is outside of the loop. Make sense? So, because otherwise we'd get a null pointer exception. Right, we'd keep going up to the end and then we would say, hey, head if we didn't have the head.next, it was just head is not equal to null. We'd get to the last item, and then from the last item, we'd go head, or last node, we'd go head is equal to head.next. So now head is pointing to null. And then we'd say head.previous, but head is null. So doing a dot previous gets us a null pointer exception. So we want to stop when head.next is equal to null, which would mean that head is the only thing in the list. So then we set head is equal to null and then size equal to 0. That makes sense? All right. Write an instance method called count. Count iterates over a linked list and returns the number of times an item occurs in the list. So for this, if I want to code this correct, usefully, then I need to have a linked list class of some kind. So let me create a new one. Linked. I'm going to call it just exam linked list because easier to do it that way. And all I need for a linked list, let's see, the objects are doubly linked, it says. So so all we need to do for a linked list is to put in the head and tail, and then we can code. So we just need to put in the instance variables and that. So let me make my own linked list. And again, I don't really need the add and remove methods here to do anything at the moment. And on the so part of this is that we are not going to be using the add and remove methods because you'll be writing something special that requires you to make your own add and remove methods. Don't panic too much about that though. All right, so exam linked list. So write an instance method called count. We need to have a node e head, a node e tail, and it's freaking out because it's like, what is the head and what is the tail? I don't know. What is a node? I haven't defined it yet, but that's the use of private classes. So private head, private tail, and now we need a int size. So it recognizes what a size is. Private int size equals 0 to start out with, and no need to create a constructor now. Everything, and now we're just going to create a private class. Private static class node e is equal to, and now we will have an e item node e next node e prev. That's all we need. Make sense? So that's all we need to get to just start coding. So now we've got a public int count. Count iterates over a linked list and returns the number of times an item occurred. So public int count e item. So int, let's go ahead and make our return value int occurrences equal to 0. Return, probably misspelled it. Yep. Okay. Says it's redundant, but that's okay. So now what we need to do is we need to iterate through using the current node. Node e current equal to head. And because even though it's doubly linked list, because we're only going in one direction, doesn't really matter. While, and then I'm not really sure what we're going to, I think though it will be while current not equal to null. It's either going to always be while current is not equal to null if you want to go and iterate if you can do this for everything, or if you need to stop to the end right at the last one, then it's while current dot next is not equal to null. So current is equal to while current is not equal to null. This is essentially our I++ statement. Current is equal to current dot next to advance one node. So anyway, while current, so what we'll do is we'll say, hey, if current dot item dot equals the item we are looking for, then occurrences plus plus. Yeah, typo in word occurrences. Copy. Oh, I really misspelled it. Boom. Like, full disclosure, I got my PhD in computer science, not in spelling or English. Okay. So this is all we need for that. So so int occurrences, node current is equal to head, while current is not equal to null. We just simply count it and we just go to the next one. What's the time complexity of this? Well, we touch each node once, so it's O of n time. All right, so here's another one. Write a static method that takes in two sorted linked lists of integers and merges them into one sorted linked list and returns it. So I'm going to go ahead and go back to our other one since this is a static method. Now, because it's a static method, we can't access the nodes in them, right? Does that make sense? If it's an instance method, that means it's inside. This means it would be outside. So let's go ahead, appearances, exit distraction-free mode. We're going to go to exam code. We've got two lists here. List A and list B of public static linked list merge. So if you've learned about merge sort, this is exactly what we're doing. So linked list of integers merged, not merged. Merged. I'll learn how to type one of these days, I swear. Return merged is equal to a new. So, okay, what is the keys here? The key here is that it's saying that these things are sorted linked lists, and it merges them into one sorted linked list. Okay, since this is a and returns it. Since this is a static method, you cannot access the nodes, and you're allowed to remove items from list A and list B. It gets easier and easier. Wonderful. Okay. Let's go ahead and assume that basically items occur only once, but it's not really going to change anything if they don't. But it's easier if we do. Okay, so let's go ahead and assume all items are unique. Okay, so what does this mean? So suppose we've got our input, we've got A and we've got list B. So we've got 1, 7, 10, and 9, and we've got 5, 6, and we've got 8 over here. Then we are and if we're merging them together into one sorted linked list, it would be 1, 5, 6, 7, 8, 9. But how in the world do we do that? What is like our algorithm for doing so? Well, the key is that these are both sorted. Okay, right? 1, 7, and 9 are already sorted. and 5, 6, and 8 are already sorted. So how do we merge them together? So to merge them together is actually fairly easy. Because we're sorted, we know that the smallest item is either going to be the first item in A or the first item in B, right? That makes sense to everybody? The first item is guaranteed to be one of the first items in A and B because they're sorted. The smallest thing will be to the left on the left side of A, and the smallest thing will be on the right side of B for each of their smallest things. So whichever one is the smallest overall will be to the left. So 1 is the smallest, so I'm just going to simply cross it out because we don't need it anymore. And I'll put it in our answer, 1. And now repeat. So what is the small? So now compare 7 to 5. 5 is small, right? If we remove the thing from the first thing in A, then 7 and 9 is all that left. So we can compare the smallest thing in A, the smallest thing in B. The smallest thing in B should go next, since it's the next smallest item. So now 7 compared to 6. 7 compared to 8. 9 compared to 8. And now we have one thing left. So all we'll do is just simply dump everything that's left in A to the end. Does that make sense to everybody? So what we do is we just constantly compare the first items until one of those is emptied out. And it says we can remove the items from the list, which is great. We'll do that. So while list.a is dot size is greater than 0 and list.b dot size is greater than 0. So while both A and B have something in them, right? We'll stop one of them once one of them is empty, and we'll burn that bridge when we get to that, when we get there, okay? So let's go ahead and see. Okay, so while they're empty, we will just simply say if, first we need to figure out which is bigger. If list A, and they're integers, so great. If list A that get the first thing in there is greater than 0, not greater than, if list A is greater than list B, and we don't have to check for equals because like we said, everything is guaranteed to be unique, but there's an easy way to solve that, which is just simply say greater than or equal to, and then it would default to anything being in list A going first. So we compare the first two. If actually I'll do less than, so less than and equal there. So if list A is, if the thing in list A is smaller, then we're going to do merge dot add list A dot get the, so we're going to get the first item from list A and add it, and then list A dot remove the item at index 0. Make sense? We can actually shorten that by just dumping this right into here, because remember, remove will return the item removed, but I like to be specific. Else, that means the thing in list B is smaller. Okay, and then it's just going to continue, right? It's going to end because we're constantly removing the thing in list A or the thing in list B. Now, what do we have? Now, that means that one of these is empty. So, but we don't necessarily know which one. We could write an if statement, or we could just be lazy. I like being lazy. Merge.add all. Wonderful method. Love it. Means add all the things in. So we're going to move. So then we're going to add everything from list A. Add everything from list B in. and return merge. And if I, yes,
Could you do that in the same statement? Merge A and B together.
I don't think so. Hey, cat, what's up? Man, the animals really like me being, like saying hello to me. Now, the reason this works is that one of these will be empty and therefore have no change whatsoever. But the other one will have the items left in it. So it will just simply tack them all onto the end. So for example, suppose we had something like this situation, 1, 2, 3, 5, and we had 4, 6, 7, 8, 9, right? And we needed to merge these two, A and B. What would happen? We'd do 1, we'd do 2, we'd do 3, and then we would do 4, and then we would do 5, and then we would end. And then we would add everything from list A, but we've removed everything from list A. So no. And then the list B, then the merge at all list B would do 6, 7, 8, 9, like that. Make sense? Runtime for this is amazingly O of n. Now, why is that? Because we're dealing with a linked list. So the removal operation over here, that is a constant time operation. Even though get is normally O of n, we're only ever getting the first item in the list. Constant time operation. So these are all constant time operations. We're working off of, if there's n items total, then that technically it's n plus m, where m is the size of B and n is the size of A, but that's a mouthful. But if we assume that they're roughly the same size, then it's going to be O of n. So, and then the add all, well, for an array list, that might be a bit of an issue, but actually to add two things to how do you combine two linked lists, right? If I've got linked list one, if I've got a linked list over here, right? And I've got a linked list over here, adding them together is pretty easy. It's just simply a matter of just adding this pointer over here, making this guy the tail, right? And then increasing the size by however big this was. Make sense? It's merging two linked lists together is a constant time operation. And this brings us actually to an excellent point for where linked lists are superior to array lists, where they do something array lists can't do, which is that linked lists are perfect if you need to split something up and then also merge it together. See, because splitting if you know where you want to split it, the actual splitting operation takes constant time. And then merging things together is a constant time operation. So linked lists are wonderful at that. Okay. Now the Uno reverse card. Write a method that reverses a doubly linked list. It will be an instant. So this is actually a classic interview question. Not that they give you a doubly linked list, where they just simply ask you, reverse a linked list. Okay. So there's a lot of ways to do that. And then what they'll do over 45 minutes is ask you progressively harder questions like, okay, great, you did it with a doubly linked list. Now, what if it was singly linked? And what if you couldn't use any variable, what if you had to do it in place? You couldn't use an external variable. So let's keep that in mind. So over here, but inside, right now we're inside our node class. We did not add so first off, if I had an add and remove, this would be trivial as anything. Okay. Because if I had an add and remove, all I would have to do to reverse it is simply create a temporary linked list, add everything into the other linked list, and then go in reverse and add it back into the original linked list, or add it in reverse like we saw with the string. But we don't have that, so I'm going to do it the hard way. So public static revert. So public void reverse. And I don't know if I've done it the hard way before. I know you can. It's annoying. Public void reverse. Okay. So I'm going to need to drag out the first thing I want to do is drag out my pen. Okay. So I've got this doubly linked list over here. And I need to reverse it. Okay, so I've got myself a head and I've got myself a tail. And at the end of the day, these pointer, it needs to be reversed. Right? So if this is A, B, C, D, E, then E should be the head and A should be the tail. But it's not quite as easy as just swapping everything around. We want the actual nodes to be reversed. So first things for very first thing I'm going to do is I'm going to just chuck this tail right over here. I'm going to say, hey, the head is equal to the tail. Or sorry, tail is equal to head. Going to make it the first item. Make sense? That way I can remember what, that way I don't have to worry about that later. Now I'm just dealing with the head. So let's go ahead and see what we can do. We can do head is equal to head.next, and that's not really going to affect anything at all. So that will move that guy over there. And how long will, and this should be in a while loop because I need to do this. So let's say while head dot next not equal to null. Okay, first thing we did was head is equal to head dot next. So that will advance that there. But again, we'll stop at the last one. So head is equal to, this will get us to the last one. Okay, so now that we're there, and notice again, I'm writing and drawing this. Head is equal to head dot next. So now we need to reverse these links. Okay, so first off, this guy doesn't need to exist anymore. He should point to null at this point. Because he would be the tail, so his next would be his next should be nothing, right? So what is A at this point? He would be head dot previous, the previous guy. You're equal to null. Head dot previous. Your next should point to null. Except we don't want it to point to null. We want it to point to, because that would make everybody's next point to null, which we don't want. Instead, we would want to say is that you should point to whatever your previous is pointing to. I know that's a mouthful. So A's previous is null currently, right? So now it will point to null. Now we need to get his previous to point, which currently points to null, to point to here. So head dot previous should be equal to But if I say head, we're going to get into a lot of issues because we're always going to point to the same node. No, we would just point to where head currently is. So. All right, I think that will do it. So let's work through it. Okay, head is equal to head dot. So we've got head is equal to. So here we've basically said head is equal to head dot next, head dot next, so head dot previous is dot next is equal to this. Head dot previous is equal to is equal to the head. So this guy's previous, which goes out the back like this, should go over here. Okay, now let's go ahead and continue on. Head is equal to head dot next. Head dot previous dot next. That should point to head dot previous dot previous. And now his previous head dot previous dot previous. There's that. That should point to head. Head is equal to head dot next. Head dot previous dot next should point to head dot previous dot previous. Head dot previous is equal to points to head. Points to this node over here. And now we say head is equal to head dot next. Head dot previous dot previous. Sorry, head dot previous dot next points to. Sorry, head dot previous dot. I overshot head dot. Head dot previous dot next. It's going to point to head dot previous dot previous. It's there, and head dot previous dot previous. Going to point to head. Okay, head is equal to head dot next is equal to null, so we're out of the loop. So head dot previous now should point to, well, we're at the head, so it shouldn't point to anything. So there we go. It's a mess. Yes. It's a mess, but with a singly linked list, it's kind of absurd. This is definitely harder than anything I would kind of ask on the exam. And full disclosure, your exam will basically be on doing operations with sorted linked lists. So just keep that in mind. Yep. So like this problem is representative of what we might see on the exam. But this one is good if you really want to make sure you understand how the pointers work. It's really hard to do unless you're really comfortable with the pointers. All right, so speaking of sorted linked lists, right? Speaking of sorted linked lists, here. So we're going to make a new type of linked list called a sorted linked list. And it's like a linked list, but it keeps all the items in it sorted. As a result, when we add an item to a sorted linked list, we don't actually provide an index because it figures out where to put it based on the items already in the list, right? You don't add it to an index, you just add an item and it's going to go and put it in the sorted location. Your task is to create that add method for a sorted linked list shown below. The method inserts a new item into the sorted linked list in such a way that the list remains sorted. So for instance, if we did 1, 2, 5, we added 1, we added 4, it'd become 1, 2, 4, 5. For simplicity, we can use either a sorted singly or a doubly linked list. Okay, so I'm going to do singly because, oh my God, that's so much easier. There's less things to have to connect. So node, I'm going to do public. You can use less than, greater than, equal to compare items. But if you remember how to use it, compare to, you can use it for extra credit. I'm just going to go ahead and assume it's integers, again, for brevity. So public, private static class node. I'm not even going to put in a generic because I'm going to simply say, I'm going to just simply say e item is equal to, not even an e, I'm going to say int item is equal to, is that, and then node next is equal to, sorry, node next. And then we're going to do, we're going to make a constructor. So public node int item. Again, I'm just going to assume I'm doing integers here because that makes it so much easier. Int, or rather, I'm going to say this dot item is equal to the item that we passed in, and that's it. Okay, and I'm just going to do a head. You may not call the get node method. You may not call the index e item, and your solution must be O of n. So basically, there isn't an add item. You have to write the code from scratch, is what I'm saying there. Okay, so we need a node e head as well. Again, I'm so used to putting in generics, but again, all we care about is that. So let's go ahead and do a public void. Oh, and I will create a size, int size, but we don't really need one. Public void add int item. And again, I'm just doing it as an int because brevity, rather than doing it with the e and the compare to. Okay. So how do I do this? So, well, we need to think of our cases first. Okay. So cases, case numero uno. We don't have anything. Oh, sorry, case. So let's think of our cases. I can think of a couple cases here. First, there is no out of bounds case, right? Just gonna figure it out. So our first case is, what if there's no item already? So first off, no matter what, let's do a size plus plus at the end so we don't never forget to increment the size. So if head equals null, boom, let's go ahead and make it. All right, equal null. Head is equal to, oh, and because it's never going to be a new out of bounds error, I can always just simply say node adding is equal to new node item. So this is the node containing the item we're adding. Very important you don't mix up the difference between a node and an item. Just got a message. Let me see if there's a fire downstairs. No, there is not. but let me respond. Mhm. Yeah, my wife is good about home maintenance, but we take the rule that if we're doing something with electricity or if anything that flows, be it water or electricity, call a person who knows how to do it. So, like she builds stuff, she's good with wood. So this dot head, head is equal to adding. Boom, we're good here. Okay, other condition. What if we're adding the very first thing? Else if, so if we're adding the very first thing to the list, right? Normally you're saying if index is equal to 0, but how would we know in this case? In this case, we would do what? We would say basically have to check, is it smaller than the thing in the head? Hey, Sean, glad to see you back.
Hello.
How's your arm?
Not sore yet, but probably tomorrow.
Hey, so let's see. If the item is smaller than the smallest item in the list so far, then that item needs to be the new head. You can also do less than or equal to, just in case it's like small, And we can do head is equal to adding dot item. Adding dot next is equal to head, so attach it to the list, and then head is equal to adding. Make sense? So if it's not the very first thing and it's not the smallest, then we are in basically the everything else case. So otherwise, let's go ahead and make a node current. Figure out where we are. That's equal to head. And then we need a while loop of some kind to iterate over this. And we're going to do current. Sorry. Okay. Node current is equal to head while current. So while current is equal to current on next. So it's either going to be current or yeah, so it's either going to be current or current is, yeah, while current. Let's try while current is not equal to null. Okay, so while current is not equal. So what are we going to do? We are going to basically say, hey, suppose we've got a bunch of nodes over here. Like I've got 9, 7, 9, 15, and I want to add 10 in. So what I'm going to do is basically I'm going to say, hey, so what can I do? I can simply say, hey, if, yes, this is what I can do. I can say, hey, if current fits between current and current.next, then put it between current and current.next. So we would just simply say, no, it doesn't. So advance it. Otherwise, so advance it. And so we would just simply say, oh, hey, is current less than current.next.item? And if it is, just attach it in. And the kicker here is that we would have to make sure that as a result, there always has to be a next item for us to compare to. So while current.next is not equal to null. Okay, so what does this mean for us? This means we need to do it like so. This means we just simply say, if current dot next dot, specifically if item is less than current.next.item, then we do our typical add thing. Adding dot next is equal to current.next. So again, if the 10 is adding, then we would just simply say current adding.next is equal to current.next. And then we would say current.next is equal to adding. Okay, and now again, draw. So I said draw. Scratch that out, move that in. And there we go. Also, because it's the only item there, whoops, because it's the only item there, at that point, we're done with the loop. So we should break out of it. Okay. Finally, if we get to this point and we are done, okay, it's possible that we never added it. Okay, so we can just simply, so we can have a flag here. So there's two ways we can do this. So we can do Boolean added is equal to false. And then we can say added is equal to true. And basically what we're saying is that, hey, if we didn't add anything, that means it's bigger than everything else in the list. So if added, or if not added, if we didn't add it, that means it's bigger than everything else in the list. We still have access to current. Oh, yes, we're in the else statement. So we still have access to current. So we can simply say, hey, current dot next is equal to add it, because it's the biggest thing, right? If we didn't add it, that means that we couldn't fit it anywhere in between any two things, right? So that's kind of our special case there. Otherwise, and again, this could probably, if we had actually made a tail, we could actually simplify this. We could probably, yeah, we could simplify this. First off, less than or equal to, if we had a tail. Another way to do that would just simply ask if it's bigger, but let's go ahead and make another case. Because that will be easier for us and it makes more sense than having way too many, except I don't like piling my ifs too deep. So let's go ahead and do a node tail. And this is going to just require a few more lines. Tail is equal to, so here when we're adding our very first node, the head and the tail are the same thing, right? Boom, we're done there. And so now all we have to do over here is add another else if statement. Else if adding dot item is greater than is greater than our tail dot item. So first we check if it's smaller than anything in the list, then we check if it's bigger than anything in the list. And we'll just simply say, hey, okay, if it's bigger than anything in the list, what are we going to do? We would simply say tail dot next is equal to adding. That will attach at the end of the tail. And tail is equal to adding. Now that it's the end of the list. And now we've got our else statement without any weird exception thrown into there. We just simply stop the loop when we add something. Does this make sense to everybody?
Do you mind scrolling up to the top of the? Okay, thank you.
All right. So like I said, the link, so start phone. Like I said, the linked list questions are gonna be on the linked list coding questions are gonna be about doing stuff to sorted linked lists. Okay, why? Because it's different enough, but it also requires the same kind of skill set. Okay, so there you go. And again, I've recorded this. I'm going to go ahead and upload this to YouTube. About how many questions will be on the exam? I think about 10, a small number. But it's time for the freebie portion of this, which is the part where I take some mercy on you poor unfortunate souls who decided to do this during the summer. Actually, I do this for everybody, but every semester. I guarantee you that this question will be on the exam. This very question, which is a list can be implemented in a number of ways. Compare and contrast an array list to a linked list. In which situations would you implement one list over another? So this will be on the exam. It will be worth 20 points. So, you know, I don't know, if I were a prepared person, I would like do that question in advance and then copy paste my answer into the exam. But I don't know. So let's go ahead and talk about this. So what are the different aspects that that we can compare and contrast array lists in? Okay. So the first and most obvious is their operations, right? So what are the list of, so what are all the operations for an array list and linked list? What do they have? More specific, okay.
An array list is dynamic.
Well, no, like what are their operations? And they're both dynamic. That's like kind of the point of a list. But what are their, so for instance, we can add to a list, we can remove to a list, we can get items from a list, we can change items in the list, right? And aside from that, and that's essentially the only things that will be different. They both have a size method, but that's constant time for both of them. So there's really not much to talk about there. So when we talk about array lists, we can really break it down into kind of three different ways they differ from each other. The first is how they use space or how they waste space. Now we'll come back to that one, but that one's important to remember, right? They use up space differently. Okay. The next one is, well, and the other ways are their operations. Now there's two paired operations, right? Or there's two sets of paired operations. You have your add and remove operations, which are, they go together. They will have the same runtimes no matter what. And then you have your get and your set operations. So let's go in reverse because that will be easiest to hardest. All right. So let's compare get and set for array lists and linked lists. So now I would want you to put some detail into your answers, not just my scribbles. Okay. You'll need to put quite a bit more than this. Okay. But no more than a couple sentences. List, no. All right, so how do array lists work for get and set operations? Anyone?
Requires an index number.
Yeah, you just use an index. Go specifically, can you go directly to an index in an array?
Would it be get and then that index?
Yeah, but can you go directly there? That's what I'm asking. Can you go directly to an array? But I mean, both of them have the get operation, which is get I, right? Which is where I is an index. But what I'm asking is, how do they differ in using that operation? So
For an
for
array list, doesn't it have to iterate through everyone, whereas a linked list can go directly to it?
other way around, right?
Oh, array list can go directly
to it,
linked list would have
because
to.
because it's got an array over underneath it. So for those of you who never had the unfortunate exposure to this, right? Let's take a look at an array of integers. Okay, this is an array of integers, index 0, 1, 2, 3, 4, 5, 6, 7, 8. Now I'm looking at an array as opposed to an array list because an array list does use an array in the backend, right? Now this is array R because just makes me sound like a pirate. Okay, so now array R, if I've got an int array R, okay, what's going on there? That means that if I say, if it's a new array, then what actually gets stored in memory is the memory location of an array. An actual hexadecimal location, dead beef. It's actually used as a signal, I believe. So anyway, or you use something. Let's go and make it something easier to add, like 0x0027, okay? So what you do, so how does the computer look up where something is? Well, this memory location, 0027, refers to index 0. So when you go ahead and you do something like array, or rather R index 3, the way that the computer calculates this is that it says, hey, what I would like to do is I'm going to take I need to calculate the memory location of that And it's actually a very simple operation for me, a computer, because it's just addition and a multiplication operation, which is just more addition. Right, so I'm going to do R plus, so the memory location of index 0 plus the index times the size of the element in my array, right? So if it's an integer, that would be 32 bits, right? And so to calculate so the long story short, again, is that no matter where the index is for an array list, for an array, I can just use a simple operation that works in constant time. Doesn't matter how big or small this is, because I don't care if numbers are big or small. It takes me the same time to calculate them because I'm a computer and gates are magic. Okay. So it takes me constant time to get something or to set something in an array, because I can just go directly to that location using this equation. The equation itself is not important. What's important is that I can go directly to. Okay, and that takes constant time. Whereas a linked list, if I want to go to a specific index, right, I have to start at one location and then I have to go and get to the next location, which means I'd have to go to the next location and until I get to the appropriate thing, right? And once I'm at the appropriate node, then I can get the value from that node or swap it out. Make sense? I have to start at the head and I have to follow and I have to do my scavenger hunt through my computer. Again, probably don't, you want to definitely put in like a couple sentences to explain this in your own words. Scavenger hunt. Oh, then, okay, there's your add. So there's your get and set. What are your add and remove operations now? So let's think about this. So there's two cases for adding to an array list, right? If I'm adding to an array list, which is filled up, right? There's two cases. I'm adding to the end, which is, and adding to the end is no problem most of the time, right? And then I'll add to the, or I'm adding to the beginning, or I'm adding to somewhere that's not the end. So let's look at the adding to somewhere not the end. If I'm adding to somewhere not the end, 5, 6, 7, right? Then what do I have to do? If I want to add 4 where 5 is, then I have to move 7 over here, 6 over here, 5 over here before I can add in the 4. Make sense? One second, I'll be right back. Hey, Annie, what's going on? It's not pizza. You don't put the silver coin. I want to make sure. I just want to make sure it wasn't doing something. Thank you. I will join you and help you. Don't worry. It's hard to tell whether the toddler's having a tantrum. So we're, well, not the 4-year-old, whether the 4-year-old's having a tantrum or he's in pain, you know. So I just wanted tantrum. My wife is working on cleaning up the house because my in-laws are coming. But he wants his mother to act as a pillow, you know, and that does not necessarily work. All right, so if I'm adding to the middle of an array list, it's gonna take O of n time to move something in the middle. If I'm adding to the end on the other, it takes constant time to add to the end, except, or rather it takes O of n time, I should say, to add to an array list, except if you're adding to the end. Except if everything is filled up and you have to copy everything over and reallocate. Right? Make sense? So it's O of n, except if you have to add to the end, except if you have to add to the reallocate. So there's a couple of exceptions there, right? Which is that is generally O of n, but there's two cases. If you have to reallocate, it's always going to be O of n no matter where you add it. If you're adding to the end, it's going to be constant time so long as you don't have to reallocate. Make sense? For a linked list, on the other hand, well, with a linked list, you're going to have a head and a tail. So it is constant time to add to the head or tail. Make sense to everybody? Okay, so adding to the end or the beginning is constant time. And just a footnote for when we're actually figuring out where we want to, which would be better for which case. When you're adding elements, where are you typically adding them? You're adding them to the end most of the time. Most of your operations, when you're adding stuff to a collection, you are adding it to the end. Less frequently, you're adding it to the beginning, and even less frequently, you're adding it in the middle somewhere. So the vast majority of the time when you're adding something, it's gonna be great. So you wanna use this, the linked list. Otherwise, it's over in time anywhere else. Don't trust the big O cheat sheet. It says constant time add for a linked list, but it takes O of n to figure out where you're gonna actually do the insertion. The actual physical adding and connecting of nodes, that takes constant time, but trying to figure out where you're going takes O of n time. Okay. And now I got to clear this because it's getting way too messy. Now let's talk about space. Space, the final frontier. I like the new Star Treks, by the way, they're good. Okay, so how do these things use space? So an array list is generally very efficient with space. You've got your array, and then you've got a memory location stored for each item that's stored in the array. But an array list can waste space, which is to say that basically you can have this space occupied by an array list, right? And then you have this capacity left over. Your worst case scenario is essentially, I've got 1 million items added to an array list, right? So this is 1 million. And then I add my 1 millionth and first item, and it's all full up. So what do? I double the size to 2 million, right? And then I copy it over, and then I add my millionth item, my million and first item. And then I don't add anything else because I'm silly like that. And now I've got 999,999 wasted spaces, right? So there's a potential to waste space with an array list like that. Make sense? However, array lists do have this funky little method that helps you with that, which is, I think it's called list.trim, which will, which if you know that you basically your array list wants to be you want your array list to be set at a certain size. Once it gets to a certain size, basically it'll shrink the capacity to the size of the array list. Basically, it will create a new array that's exactly the size of all the space you're occupying, and then it will transfer everything over. Make sense? So you can basically make sure that you're using only the array space you want to. Now, a linked list, on the other hand, has quite a bit of overhead. Now, you're not going to be wasting space in the same way, but you're going to be using space because you've got your node, right? And the node has an item. And then, unlike it, it has to have the next and possibly the previous. So whereas the array list was using one memory location's worth to keep track of items, this is using 3 memory locations worth. One to keep track of the item, one to keep track of the next item in the list, and one to keep track of the previous node in the list. Next node, previous node, not next node. Make sense? Okay. So any questions? Okay. So that is it for the practice exam. Now, let me stop recording.